Hello, can everyone hear me on Zoom? Okay, it seems like no one's saying anything in the chat, so I'm gonna say we can go ahead and get started. Who's up first? Let's go ahead and make sure it's unmuted.
Right. Hi, everyone. I'll be going over recursion and pre-recursion. So the idea of recursion is to solve a problem. The idea of recursion is to solve a problem by continuously dividing the problem into subproblems and then combining these results to solve your main problem. A common example that all of us have seen where we use recursion is computing the factorial of a number. So let's say we want to find the factorial of 5. You'd basically be doing 5 times 4 times 3 times 2 times 1. But another way to look at it is you can, in order to find the factorial of 5, you can multiply 5 and the factorial of 4. And in turn, to find the factorial of 4, you multiply 4 by the factorial of 3. And it goes on. Finally, you'll reach factorial of 1, and you already know that the factorial of 1 is 1. So here, in order to find the factorial of a number, you're dividing it into smaller problems where your subproblems are basically the factorial of a number 1 less than your previous number. Another example is the Fibonacci sequence. So here, every term of the sequence is the sum of the previous 2 terms. So in order to find, let's say, the Fibonacci, term number 3, so then you'd be adding the second term and the first term. So let's look at the structure of a recursive function. A recursive function has 2 parts. The first part is the base case. The base case is leads to the final return value, and it's when the function terminates. It's the smallest case of the problem. So from the previous examples, let's take the example of the factorial sequence. Then computing the factorial of 1 would be your base case, which should return 1. For the Fibonacci sequence, this would be the term at term at 0 or the term at 1. Your next part is the recursive leap of faith, or the recursive case. This involves breaking the larger problem into a smaller problem that you will eventually lead you to the base case. And pre-recursion is just a more complex form of a normal recursive function. This involves dividing the bigger problem into multiple recursive calls or multiple smaller subproblems. So here's a general approach you can use for any question on recursion. This involves asking yourself 3 questions. The first one is, when do we stop recursion, which is basically your base case. So for the factorial example, our base case would be when the number is 1. Another example is when you have any question which uses list processing. So you'd want to stop when your list is empty, or in other words, when you reach the end of your list. And for integer processing, which basically involves using floor div in order to get the rest of your number, you'd want to stop when your number is 0. So let's say you have the number 456, and you want to add the digits of that number. Then you'd be doing floor div in order to get the rest of your number, and using the modulus to get your last digit. So when you have 456, when you do floor division first, you get 45, and then you get 4, and finally you get 0. So this would be your base case. However, note that these are common base cases, but they may vary depending on the problem. The second question is, what is the subproblem we can divide the problem into? So for factorial, this would involve taking the factorial of n minus 1. And for the Fibonacci sequence, this involves calculating the term at n minus 1 or n minus 2. And finally, once you have your subproblems, you need to combine the results of these subproblems. So for factorial, you'd be multiplying n times the factorial of the previous number or one less than that number. And for Fibonacci sequence, you'd be adding these two numbers because Fibonacci sequence is basically every term in the Fibonacci sequence is the sum of the previous two terms. So you'd be adding the term at n-1 and n-2. So now let's look at tree recursion. Tree recursion is just a more complex form of a basic recursion question. So this involves making more than one recursive call. This allows us to explore more possibilities and outcomes, and in turn, it leads to longer runtimes. Most of the tree recursion questions also involves using some built-in functions like max, sum, and min. These could help you to solve your questions. And I'll also go over some common mistakes for questions on recursion. First is the use of an incorrect base case, return type, or value. So let's say a function is asking you to return a list of lists. So the base case should then be returning a list of lists so you'll be returning a list containing an empty list. For the number processing problem, the base case need not always be returned 0. So for example, for the factorial problem, you'd be returning 1 when you hit your base case of the input being 1. Another common mistake is not taking into account the order of base cases. So for some questions, you could have more than one base case. In that case, you need to decide which base case you'll be having first. So let's say you have a question which involves strings. So you may have to check if the string's length is 0 before looking at the string's first character. And finally, another common mistake is forgetting to combine the results of recursive steps. So for example, returning factorial of n-1 rather than multiplying factorial of n-1 with n. So on an exam, a common way to approach is first approach the problem in the order that feels most intuitive for you. So this could be first figuring out the base case, then working on the subproblem division and the combination step. Or you could also go the other way around. You can first do the recursive case and then go back to the base case. Feel free using both the approaches and then do some practice questions and use the one that you're more comfortable with. And test problems are often divided into base case and recursive step parts. So even if you don't understand the entire question, or if it seems to be very complicated, or if you're on a time crunch, you can always aim for partial credit. So you can look at the base case alone or the recursive case. Do you have any questions before moving on to the previous exam questions? All right. So first we'll be doing this previous exam question from summer 2022. So implement blob sum, a function that takes in two positive integers n and k, and returns true if there exists a way to add together the digits of n to equal k, where every digit of n is used exactly once. So however, in blob sum, multiple consecutive digits can be considered as a single multi-digit number, a blob, or as multiple individual digits. And also digits are read left to right. So for example, if you have the number of 123, you can blob sum it to 15, 12 plus 3, but you cannot do 1 plus 32. So digits have to be always read from left to right. And this question also says that you can assume that count underscore digits is implemented correctly. So count digits is just a function which returns the number of digits that a number has. However, just note that the number 0, in this case, we are considering that the number 0 has no digits. So that will be returning 0. So I'll be going over a couple of doc tests here. So blob sum of 123, it could return 6 when you add up every single digit. So 1 plus 2 plus 3. In order to add up to 15, you could do 12 plus 3. However, you can't add up to 33 because the digits of n must be read left to right. So you can't do 32 plus 1. Yeah, that's pretty much it. Here's a skeleton code for the question. Take like around 7 to 8 minutes to work on this question. I'll start going with the solution now. So first, if you look at this question, there are multiple ways we can blob sum a number. So if you have the number 1, 2, 3, either we can add all the individual digits. So we have 1 plus 2 plus 3, which would be 6. Or another way to blob sum it would be to do 1 plus 23 or 12 plus 3. So however, if you have a very large number, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, your blob can have more than 2 digits. So your blob can be anything like 7, 8, 9, or just 8, 9, or it could even be 2 all the way till 9. So you can see that there are multiple possible ways that you can blob sum it. So intuitively, this would involve using tree recursion. So first, you have the base case here, and there are 2 possible base cases. And then the question also has 2 variables, rest and last. So the first thing that you can solve is trying to figure out what rest and last could be. So rest intuitively would be n floor division by 10. So this would give you the rest of the number. And the last, in order to get the last digit, you'd be doing n mod 10. And now you have another variable called new underscore blob. So new blob is basically when you're, let's say you have 123 again, and your last was the number 3. And in order to add 2 to the blob, in order to make it 23, this is where you'd be doing that. So here, because it's just a 3-digit number, you'd be doing 3 plus 2 times 10 in order to get in order to get 23. However, if you have a bigger number, let's say now you have the blob 23 and you want to add 1. So you'd be doing 23 plus 1 times 100, so which is 10 square. So in order to basically get 10 to the power of whatever number you need in order to add it to the blob, you'd be doing blob plus last times 10 to the power of count underscore digits of blob, because the question mentioned that you could use the function count underscore digits, which would return the number of digits that that number has. So if your blob is 23, then it has 2 digits. So if you're adding another number to it, then you'd be doing 10 to the power of the number of digits that the blob has, and you'd be adding the blob to it. So that would now give you your new blob. And now there are 2 possibilities. Either you add your last to the blob, either you add your rest to the blob, or make a new blob. So if you have the number 123 and your blob is the number 23, you can either add 1 to the blob, make it 123, or you could just do 1 plus 23. And this is where the tree recursion comes in. So returning helper of rest, k minus new blob and 0 would be the case where you're creating a new blob. So your rest would be the remaining number except the last digit, and k minus new blob would subtract your current blob from the target value that you need to reach, and you're making the blob 0, so you can start building a new blob. And the other case is when you have you're again taking rest, k, and a new blob. So this is when you're adding another number to the blob. So this would involve, let's say, having 23 as your blob, and then you want to add 1 to the blob to make it 123. This case would give you that. And now combining both the subproblems. So you could either add, multiply, use, or, and, or any of those statements. So for this, you'll be using or, because you need to find if any of the blob sums add up to the value k. So you'd be checking if either of these returns a true value, and you'd be returning true. Now coming to the base case, one of them would be if n is equal to 0, then you wouldn't be returning true right there, because you also need to check if k is equal to blob. Another case which would be returning false would be when k is less than equal to 0. This is because this is basically when your sum is less than the target sum. And finally, you have blank g. So here you'd be calling the helper function. So you can see that the helper function takes in 3 arguments, n, k, and blob. So since your original function blob sum is taking n and k, you can just put in n and k for the first 2 arguments. And for blob, since you're starting you're creating a new blob, since you have 0 as your blob right now, you'd be taking 0 for that. Any questions on this?
Can you explain new blob again?
So just in summary, this question involved using tree recursion, where you need to consider two cases. One where you're creating a new blob, or the case where you're just adding the number to the existing blob. Oh. So one of the questions is, instead of using count digits, can we use the length of blob instead? Since we are taking a integer, I don't think we can use length of blob. Another one is, why is it k less than equal to 0 and not k less than 0? Okay, so if k is even if k is equal to 0, you need to be returning false, because in that case, there's a possibility that not all the digits have been used. So the question also says that you need all the digits of your given number n have to be used in order to add up to k. So let's say you have the number 123, and your target sum k is just 2, then it should be returning false, because just giving out 2 should be returning false. Or if, let's say, the target sum is 5, so then it would be 2 plus 3. However, 1 wouldn't be used in that case. So then you should be returning false. All right. Okay. We'll be moving on to another recursion question. This is from the midterm 2 of fall 2022. So here we have basically this implementation of a hydra. So a hydra is represented by a tree, and each head is represented by a leaf labeled 1. And each non-leaf node has 2 branches, and it is labeled with the number of leaves among its descendants. So for example, here's a 6-headed hydra named Learner. So this tree has a root value of 6, because it has a total of 6 leaves, and each leaf itself has a label of 1. So if you look at the left branch or the left subtree of this hydra, this has a value of 4, because this subtree here has 4 leaves. So that's the reason why this root here has 4. Similarly, 2 here. And then you're given this function is hydra, which basically returns true if the if t is an if the tree instance t properly represents a hydra. So now we have to implement this function called chop head. So if you're if you're chopping one of the leaves, then the hydra would basically transform into this on the right hand side. So you'd see 2 new heads appear there, and also all the ancestor labels are updated. So let's say you're chopping off the leaf second from the left. So you'd be replacing this 1 here with a new tree consisting of a 2 and having 2 branches or 2 leaves, 1 and 1. So you need to implement a chop head hydra, which takes as input a tree instance hydra and a positive integer n. It mutates hydra by chopping off the nth head from the left, adding 2 new adjacent heads in its place. Another thing to note here is that n here is 1 indexed. So if we say n is 1, then you'd be chopping off the leftmost head, and if n is 2, you'd be chopping off the second one from the left. And this is the skeleton code here. Along with that, so for blank A, you need to be selecting any of these options, and for B, C, and D, those are free response questions. And the question already checks if the input tree is a hydra, and it also checks if n is greater than 0 and if n is less than equal to the hydra label. So in this case, if n is equal to 6, you'd be chopping off this leaf here. However, if n is equal to 7, then the function wouldn't be, you wouldn't run the function anyway. Okay, takes like around 6 to 7 minutes to work on this question. Okay, let's go over the solution now. So if we look at this process of chopping the head, we'll see that this involves solving three sub-problems. So first, once you're given the n value, you need to figure out which leaf to chop off first. And then you need to substitute that leaf with this tree here, which has a root label of 2 and 2 branches, each having the labels, each having the label 1. And then your third step would be to change all the values here. So all of these, you'd be adding 1 to all of these labels here. Okay, so this part here, if hydra dot is leaf, this can be used to solve the first problem where you're trying to, sorry, this can be used to solve the second subproblem. So if you find once you find the leaf, so once you find the leaf here, you're substituting it with this tree here. And this is a, this is a multiple choice question. So you need to select all the options which could be right. So let's go over option 1 first. So you're saying that hydra is equal to a tree containing 2 and branches 1, 1. Initially, this may seem like it's right. However, you need to also ensure that you don't lose your pointer to that particular hydra. So first, your initial hydra would be just the leaf 1. However, if you say that hydra is equal to this new tree, then the point of hydra would be pointing to this new tree. So your the initial hydra would just remain, your initial tree would just remain 1. So option 1 would not be right. And now going to option 2. So for I in range 2, hydra dot branches dot append tree 1 and hydra dot label is equal to 2. So this would be right because you're saying you're creating a new tree which has the root 2, since hydra dot label is equal to 2, and then you're adding you're appending a tree consisting the label 1 to the branches. So when I is equal to 0, you'd get this first leaf here, and when I is equal to 1, you'd get the second leaf, and then the for loop would terminate. So option 2 would be right. And then option 3, you're saying hydra dot label is equal to tree of 2. But however, you know that the label has to be an integer and not a tree instance. So for that reason, option 3 would be wrong. Now going to option 4, you're saying hydra dot label is equal to 2. That's right. And hydra dot branches is equal to a list containing trees of 1 and 1. Again, this would be right too. So option 4 would be right because hydra dot label is equal to 2 is creating, is changing the value of this label here. This one would become 2. And then hydra dot branches is equal to this, would create 2 new branches here and would give you 1. So option 4 would be right. And finally, option 5, you're saying hydra dot label is equal to 2, again, similar to option 4. So that would be right. However, if you see hydra dot branches, now hydra dot branches is equal to tree of 1 times 2. So here, initially, this may seem to be right again, but however, this wouldn't be right because you're creating 2 copies of the same tree. So when you have tree of 1, this would create a tree consisting of the label 1. And when you do times 2, you'd be having you'd be creating a list having 2 elements, and the second element would be pointing to the same tree. So both the first element and the second element would be pointing to the same tree consisting 1. So for that reason, only option 2 and option 4 would be right. So with this part, you solve the problem of substituting this 1 with this tree. Now you need to figure out which leaf you need to chop off. So if you look at this diagram here, let's say n is equal to 5, and you're starting here. Since each label here is equal to the number of leaves that subtree consists of. So if n is equal to 5, and you know that this is equal to 4, so this subtree here would only consist of 4 leaves. And since 5 is greater than 4, your 5th leaf from the left should be on your right subtree. And similarly, if n is equal to, let's say, 2, then you'd be first checking the left side subtree. The label is equal to 4. So 2 has to be on the left side. And now you check this subtree here. Now n is equal to 2 again. So you'd be doing, you'd be checking that this label is equal to 2. So your second leaf from the left would be in this subtree here. And finally, you'd be getting this. However, if you want to go to the right, then we can take the case where n is equal to 5. So since this is equal to 4, you can subtract 5 and 4 to get 1. And then you can check the right subtree. So now for this subtree, 1 from the left would be this one, which is the fifth leaf from the left for the entire tree. If we look at the skeleton code here, the blanks, you'd see that we can use blank C and D to solve this problem. So you can say if n is greater than the left label, then you'd be chopping off the leaf from the right subtree. So that's the reason you'd be doing chop head of right and n minus left label, because we saw the case where n was equal to 5. So you'd be subtracting 5 from 4, and then you'd get 1. So you'd be taking the left first leaf from the left for the right subtree. And your else case was just chopping off the head from the left subtree, and n would just remain the same. And then you also see that there's this extra blank here, blank B. You'd be using this to increase the label by 1. So as we saw here, when we are substituting this leaf here with this tree, you're also adding all the, you're adding 1 to all the labels in this path here. All right, so your first part involved substituting the leaf with the tree. Your second part involved adding 1 to all the labels. And finally, you're checking you're finding which leaf to chop off. Right. Any questions? Right.
All right. Let's move on to the next topic. We'll be going over lists, mutability, and dictionaries, and then I'll go over runtime after that as well. But first, let's get started with lists. So a list is a basic kind of container that can hold different kinds of elements, and you create them with square brackets. You can see in this example here, you can put different kinds of elements in the same list. For example, there's an integer, a string, and another list inside of this list A here. Okay, let's review some basic operations. We can index, we can kind of count through the elements of a list by referring to its index. And remember that lists are 0 indexed, meaning that we say the first element is index 0, not 1. So for example, A0 here would get the first element, which is 1. We can call length on a list to get the length of the list returned as an integer. And we can also concatenate lists by just using addition, like a list plus another list. And this creates a shallow copy of the two lists combined together. More on that later. Yeah. To check if an element is in a list, we can literally just say x in list. And this will return a Boolean value, true or false, based on whether or not this element is in the list. And if we want to ever iterate through all the elements in the list, we can use a for loop. All right. Any questions so far? This is mostly review. Okay, cool. Okay, list comprehensions. So sometimes we want to create like a new list based on some iterable in a single line. And to do this, we can use a list comprehension. So the format of a list comprehension is, so you have your set of brackets, just like a regular list. And then you have this format, expression for element in iterable. And then there's an optional if condition. So the expression is just every element that's being added to our new list. And the element is the name we give for every current item that we're iterating over in the iterable. And so that brings us to the next part. The iterable is what we're iterating over to construct our new list. So this is usually like another list. A lot of times we'll do something like range and pass a number. That could be an iterable. And then optionally, you can have a if condition if you want to filter only certain elements to put in our new list. So when we're working with lists, there are two kinds of ways we can kind of modify them or kind of work with them. There's mutative ways and non-mutative ways to functions that will modify lists. So mutative ones are the ones that actually directly modify the list elements. So you can add or remove an element from a list or directly change one of the elements. If you were to draw the environment diagram for it, this is when you have your box and pointer diagram and you'd like actually change a value in that box and pointer diagram. But we also have non-mutative operations that don't change the original list. And these usually, not usually, these create a shallow copy of the list. And we'll see some examples of these non-mutative operations. Okay. But first, let's start with reviewing some of the ones that do mutate the list. So there's list.append element. So append always adds a single element to the end of the list. That's something to keep in mind. You can't add multiple elements with a single append. If you want to add multiple elements, you can use extend. And then if you use list.extend, you should pass in another iterable. And what it does is it concatenates all the elements in the list that you pass in to the end of the original list. So you have to notice that the difference in the argument between append and extend. In append, you need to pass in, you can pass in any element, but for extend, you have to pass in an iterable. Okay. It's also list.pop. And what this does is it removes the element at the index you pass in, or if you don't pass in the index argument, it will just remove the last element. And then after it removes the element, it will also return the element. And this is the only operation out of all of these that will return something. All the other mutating operations will inherently return none. Okay. If we want to remove an element without having that return property, then we can just say list.remove element, and that would just remove the element from the list without returning anything. If we want to insert something, we can say list.insert, pass in an index and element, and that will insert that element at that specific index. Okay. Next one, list plus equals list. Okay. This one's a little confusing because a lot of people will think that list plus equals list is the same as list equals list plus list, but it is actually not. A list plus equals list is the same as list.extend list. So it is mutative, and it will just extend all the elements of the list to the end of the list. List equals list plus list actually creates a shallow copy. So that's something to watch out for. And you can directly modify certain elements at a specific index of a list if you just say like list index I equals X, and that changes the element at that index to be whatever X is. Any questions about any of these? Mm-hmm. Flat. Yeah. So it basically, if when you do, it's the exact same as list.extend. So if you're you pass in the list is like, it has its brackets, it has elements, those brackets are removed and every element's added individually. All right. So let's talk about the non-mutative operations. So if you just call list on an iterable, this basically creates a copy of the list with the same elements. If you say do concatenation, which I mentioned earlier, you say like list 2 plus 1, 2, 3. This just creates a new list with all the elements of list 2 and then the elements 1, 2, and 3. And this is separate from both the original list 2 and the 1, 2, 3. Okay. If you do lists, you can also do list times n, where n is an integer, and it'll create a new list where you repeat the elements of the original list n times. Slicing. Slicing also is non-mutative. It will always create a shallow copy. And you can slice it from index j inclusive to, sorry, index I inclusive to index j non-inclusive. So both I and j are optional. If you leave them out, if you leave out I, it will start from the very beginning of the list. If you leave out j, it will go all the way to the very end. There's also an optional step argument for a third one. And this basically, if you put in a step, then it will like jump that many every time. So like if you do step, by default, step is 1. So it just gets you every element that you're slicing through. But if you set it to 2, for example, it would get you every other one. If you set it to 3, every third one. Yeah. And you can also use slicing to just create another copy. It's the same way that you can call list on an iterable, and you just don't pass in I or j, so it just slices the entire list. Okay, so more about this shallow copy. So what this means is that whenever we create a shallow copy of a list, we copy over all the elements of the list as they are. And what this means is that primitive values like strings or numbers, they'll get when you draw the new box and party diagram, they'll get copied over. But if there's like a nested list, then what's going to happen is that the pointer to the list is going to be copied over. It won't actually create a new copy of the inner list. So for example, here, we can see that when we create a copy of this CS and then list containing 61A list, that CS and A they all have like new entries here. But for this nested 61 list, what we did is we just copy over the pointer instead. We don't create a new copy of this list containing 61. Okay. All right, so here's a practice problem with environment diagram, box and pointer diagram. And I'll give you guys a few minutes to work on this, and then I'll go over it. All right, that might not have been enough time, but we're running a little behind, so I'm just going to start going over this one. Okay, so we start off with this list containing 3, 4. And then we see what happens after running line 2 is we added one element to this list. And what is this element? Well, it seems to be a pointer to another list. And this list is pointing back to our original S. So our first blank here will just be s.append a list containing S. And so the reason that it's a list containing S and not per se just like s.append S is if it were s.append S, this arrow here would be pointing back to the original list. But we see that it's not, it's pointing back to another list, which is then pointing back to our S. So that's why we have to create a new list here, which represents this one. And that's why we have this these list brackets around this S. All right. Okay, let's look at the next, what happens next. Well, we see that our new list we created suddenly has 2 new elements. One of them is 4, and one of them is a pointer back to this new list. Okay, so when you see that we've added 2 elements at the same time, you know that we can't be using append here because append only adds a single element. So we are actually, this should tell us that we have to use extend here because extend allows us to add multiple elements at the same time. Yeah. And what are we extending? We're extending this list here. And this list is our S index 2 because you can see our S index 2 is this pointer, which is this list. Yeah. And then what do we add here? You can see that what we've copied over is a 4 and a pointer back to this list. And where do we see a 4 and a pointer back to this list? Well, that's actually just this element and this element of our original S. So to get that, we can just slice S from the index 1 element onwards, which was this 4 and this pointer here. One thing I will note is that another possible answer here is that you could, instead of slicing S here, you could say, you could pass in a list here containing 4 and then S2 again. Basically construct this yourself without using slicing. That's also acceptable.
Oh, so you're saying you can also do like bracket S1, S2. That also works.
Extend here. You can do bracket first 4 to get this 4. You can create a new list here instead of like when you slice S, this creates a new list, right? You can manually do it without slicing by creating a new list that has first element 4 and second element S index 2, because S index 2 gives us this pointer back to this list.
Yes, you can do S index 1, S index 2 in the brackets. So
S in the brackets, S index.
yeah, right.
Is-
Because S at index 1, that's 4, and then
Oh yeah, you could, because that X index 1 would give us 4.
Okay.
Yeah. So yeah, I gotcha. Yeah, that works. Yeah.
Just to clarify, if you pass in 4 and that's with brackets 2, but it's going to extend, you have to put brackets on that whole thing.
Yes, if you because in extend you have to pass in an iterable, and if you have like the 4 and then the S2, these 2 elements you need to make sure they're put into an iterable, so you would need like a set of brackets around them to make it into a list. Yeah. Okay. So for our final step here, you can see what happened. Well, our pointer here is no longer pointing to this list. It's now pointing to this new list over here. And what is this list pointing to? Well, it's pointing to the list we created earlier. And this list we created earlier, you notice that it was originally these 3 elements, and now it's only 2 elements. So we've removed one of the elements. But we don't want to use remove here because remove returns none. And you can see that we actually want to keep like this value here. because it's a pointer to this list. And you can see that this here is also a pointer to this list. So instead, if we call s2.pop, what that does is it pops off this element. And then after it pops it off, what we do is we put it into a list here, and then we assign it to S2. So this step is a little bit convoluted, but if you follow what's happening here, S2.pop will remove this, and now we have a floating pointer here. Okay, why is this not just S2 equals S2.pop without this list? Well, here we created a new list. You can see this list didn't exist before. It's similar to how we had to create a new list up here. We're also creating one down here. And to do that, we need to make sure that we have this extra set of brackets around S2.pop. So now S2 is pointing to a list, which points back to our other list.
Would it be valid if we did square bracket s index 2 and another index like slice to 2?
Oh, so S2 and then
Take the first two elements of it.
sorry, can you repeat that one more time?
Okay, so there's gonna be square bracket
Mm-hmm.
s index 2.
S index 2, so that gives us this.
Yes.
Mhm.
And we slice it like till like first like and get the first two elements. Like slice everything until 2.
Mhm. Yeah, so that will work for cutting this down into this. The problem with it is that it doesn't do the second part, which redirects this pointer here to this thing, right?
Yeah, but if we did it all in square brackets.
They're all in square brackets. S2 is a list containing a pointer. That work? Oh. I can't okay, if yeah, that might work if so I can't figure this out in my head right now, but I suggest maybe run it in PyTutor, and then if it results in the same thing, then it should work. Yeah, I remember this problem did have multiple solutions. So all right, how are we doing on time? Doing all
I
right?
have a
Okay.
question.
Okay, here's another question. It's a list comprehension question, and like 2 minutes to work on it, and then I'll go over it. I'll start talking about it now. I probably should have walked through the doc test first. That's my bad. But yeah, so essentially what this is near function is doing is it returns whether the input S is a near increasing sequence. And what near increasing means is basically is that every element has to be more than all the elements before it, except for the element right before it. So you can see these here, these are all increasing normally. So this is true. These here are also near increasing because even though 4 is less than 2, I'm sorry, 2 is less than 4, it's right before it, so we don't care about it. And it's the same thing here and here. This is not because 1 is less than 3 and 3 is not right before 1. And these are all examples where you can see that for some element here, there's an element at least 2 spaces before it that's more than it. Okay. All right. So here is the solution to the problem. And basically, we're given a one-liner, so we have to do this and we have to kind of utilize a list comprehension here. So we have return all. So all will return true if every element inside of the list you pass in is true. So what are we checking? We're checking for every element if it's more than all the elements before it, not counting the element just before it. And so the way we're going to test for that is we're going to get the element by indexing SI. And then we're checking that it's more than all the elements before it, except for the last one, the one right before it. So the way we do that is we call max on S indexed up to the I-1th element. So S indexed to up to the I-1 element will give you all the elements up to, but not including the last one right before it. And then if it's more than the max of them, then it's more than all of them. Oops. And then for what I do we want to check? Well, we need to check, we don't have to check the first element because there's nothing before it. And we also don't need to check the second element because there's only one thing before it, and that one isn't counted for when we're talking about near increasing. So we start from the third element, which is the element at index 2, and we go to the end of the list. Any questions about this one?
Oh, I have a question about.
So next we'll talk about dictionaries. Dictionaries are basically like lists, but instead of individual elements, we have these key value pairs. And every key must be unique. And keys also cannot be mutable types like lists or other dictionaries. And if we want to get a value of a value of a key value pair in a dictionary, you can just index in using its key, and it'll give us the value. You can see here we would do dic name and then key here. And if we iterate over a dictionary, it basically iterates over the keys automatically, not the values. So some methods that we'll use with dictionaries, we can call dict.keys or values to get a list of the keys, or iterable of the keys, or iterable of the values. Or you can call .items to get iterable of a bunch of tuples containing the key value pairs. And we can also use dict.get, and then we pass in a key and a default value. And what it does is it returns the value of the key that you pass in. And if we can't find the key, then it will return default value. So let's do this problem. So we have a function memory store that returns two functions, add value and times seen. So when we call times seen on var1, what it does, it returns the number of times that add val has been called on that specific var1. So it's a little bit of a mouthful. We can just walk through the doc test and it'll make a little more sense. So we call memory store, and then we call add val 4. And then we call add val 3 times with this for loop. So then time scene of 3 is 3 because we called add val 3 times. Time scene of 4 is 1 because we called add val once. And times a scene of 2 is 0 because we never called add val of 2. And then if we call add val again, then times scene of 3, if we call add val in 3, times scene of 3 will increase from 3 to 4 because we just called it again. Okay. I'll give you guys about a minute to work on this one. All right, I'll start kind of talking about kind of the structure of this code. So we see that we create this dictionary, empty dictionary called memory. And then we have our add val here. And let's look at its structure. So we pass in var1. So if var1 is in memory, then you can kind of see here what we're doing is we're increasing, we're somehow increasing like its memory of how many times we've, if it's in the memory, then we increase it by 1 because we call add val once. Otherwise, we do something here. And then when we have time scene, we have this one line return statement. And let's start filling in these blanks. So yeah, I probably should have zoomed in earlier. My bad. But all right, we actually what we're going to do is we're going to fill part B before part A. So if we look at this conditional statement, the first part is kind of checking if we've already seen this var1. But if we haven't, then what we're doing is we're creating a new key value pair to kind of indicate that, okay, now we've seen this new var1. And the first time we see it, it gets set to 1 because that's the first time we've seen it. Okay. And then from there, this part A kind of flows from it directly. If we've already seen it before, then what we're going to do is increase our value of the key value pair by 1. So this the value corresponding to the key var1 in our dictionary memory, we're going to increase it by 1. Okay. And then for time scene, all we need to do now is access our memory. And we can do that by doing memory.get var1 with a default value of 0. Okay. One thing to note here is that we cannot just say like memory index var1 here, because that will give us, that'll work if we've seen it before. But if we haven't seen it before and it's not in the dictionary, by default, if you try to index it for index the dictionary for a key that doesn't exist, it will return none. And we don't want to return none. We want to return 0 because 0, you can see here, we want to return 0 here to indicate that we've seen it. We've called this thing 0 times. And so that's why we use this dot get instead. So then we can either return the value or 0 otherwise. Any questions? All right. All right. So next topic is efficiency. And so efficiency / runtime, basically the point of an efficiency problem is to measure how long for a function takes how long it takes for a function to run in terms of the size of the input into the function. And so the way to measure it is basically you want to count how many operations occur during this running of the function. Okay, so these are the different levels of kind of runtime. We have constant, logarithmic, linear, quadratic, and exponential. And these are in order of increasing time. So constant is the fastest and the best, or I'm say best, it's the fastest, and exponential is the slowest. So a constant time function will always run the same number of operations. A logarithmic one, if you increase the input, it will perform more operations, but the rate at which the number of operations increases is slower than the rate at which the input increases. So for example, if we were to maybe double or triple the size of the input, it would only take maybe 1 more operation. That would be log time. For linear time, the number of operations and the size of the input, they grow at the exact same rate. So if you tripled or doubled the input, the runtime or the number of operations would also double or triple. Quadratic is like the opposite of logarithmic. The number of operations is proportional to the size of the input squared. So if you were to double the size of the input, then the runtime or the number of operations would like quadruple, like 2 squared. Yeah. And usually quadratic ones, you'll see nested loops, nested for loops. And this is usually a good sign to see that it's quadratic time. Exponential is the worst, and this is when the number of operations that a function takes is proportional to some constant to the power of the size of the input. So this would be like, if this one was n squared, then this one would be like 2 to the power of n. And this normally, these tend to be tree recursive functions where you have like this really, really wide branching. And then every time you increase the input by 1, the number of operations will double, for example. Okay. So I think the best way to practice runtime is to just look at some examples. So let's start here. What is the runtime of this function? Anyone want to take a shot at it? Not, that's okay. So what we have here is we have a function mystery and we pass an n. And then for I in range 10,000, we print n. So no matter what this n is, this function is going to take 10,000 operations because that's how many times we're iterating through this. And then every operation, we just print something. So the runtime is not dependent on our n here. So this would be a constant time function. Some questions? No. Okay. All right, let's look what we have here. So we have a equals 0, and then we have for I in range n, for j in range I to n, a plus or equals 1. Okay. Anyone want to take their hand at this one? Quadratic, right. That is correct. So one thing you can look out for is you see like a nested for loop here. That's usually indication that it's going to be a quadratic time function. And one thing I will point out is that a lot of people might get tripped up by this for I to n thing. And instead of like just saying for range n, if it was range n here, so it's range n here, right? So this outer loop will run n times. This inner loop runs from I to n, right? So the first time it's going to run n times, but then I gets incremented by 1, right? Then it's going to run from like 1 to n, then it's going to run from 2 to n, 3 to n, etc. So you can see that this inner loop isn't always running n times. It's running n times, then n minus 1 times, then n minus 2 times, essentially. And then on the last iteration, it will only run 1 time because I will eventually reach n. So why is this still n times n or quadratic? Well, one property to remember is that if you do 1 plus 2 plus 3 plus 4 dot 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 plus n, because that's essentially how many operations we're doing here, right? We're doing n operations, then n minus 1 all the way down to 1. This is actually a n squared operation or a quadratic operation, because I think there's an arithmetic formula you can use to prove this. It's like the sum of positive integers up to n is like n times n plus 1 divided by 2. And when talking about runtime, we don't care about like constants, or so like that divided by 2, it doesn't really matter. So you have like n times n plus 1, and that n times n creates an n squared factor. So overall, this is still going to be n squared, which is a quadratic. Yeah. So don't be tripped up by this I thing. It's still quadratic here.
Oh, what if the I is
Like a constant. Okay. If I is a constant here, it still will it will still be O of n's. It will still be a quadratic, because let's say like we put 5 here, right, instead of I. So this outer loop will run n times. This inner loop runs n minus 5 times, right? So then you have n times n minus 5, which is like n squared minus 5n. We only care about the largest term, which is the n squared, and that still leads us to a quadratic runtime. Good question. Yeah. Okay. Right. So this one's a little interesting. We start with we pass an n, we have I equals 1, and then we have while n, we do I equals I times 3, and then we floor div n by 3. And at the very end, we return I. Anyone want to take a guess at this one? Logarithmic. Right, so this one will be logarithmic. And to see why, you can see that if we like triple n, for example, the number of operations is only going to increase by 1, because every time every time we divide our input by 3 here. So you can see that like our input would have to grow faster than our number of operations. And one way to like look out for when you're going to see a logarithmic function is when your input gets divided by some constant. For example, if this were 2, it would still be logarithmic. And that's because like you can think of it as you would have to triple or double the input just for one more operation, or like one more iteration through this loop. And that's logarithmic. All right, so how are we doing on time? All right, well, we'll wrap it up here. This question is not too important. Actually, no, I shouldn't say that. You can do it in your own time, and we'll move on to the next topic.
Okay, well, that timing works great. Okay, so hi everyone, I'm Steven. I'm going to be talking about iterators and generators. So let's start with iterators and iterables. So an iterable is just anything you can take items from one at a time and in a fixed sequence. So an example of this are lists, dictionaries, strings. All of these are built-in iterables that you can iterate over. For example, you can take items from a list, keys from a dictionary, characters from a string. And one trick is if it fits in for I in blank, then it's an iterable, and then I is the current item that you're taking from the iterable. So if you call iter, the iter function on an iterable, then you'll get the iterator of the object, and you can think of that as sort of a bookmark. And one tip is that you can have multiple bookmarks for each iterable. And iterators return their items one by one using the next function. So the first next call yields the first item from the iterable. Then you can call next again on the iterator to get the next item and so on. And then iterators are also iterables. And then it'll return a stop iteration exception if you call next when there is no next item. Generators are kind of an extension of this idea. Generators are a type of iterator that are defined as functions. They're kind of similar to normal functions, but they replace return with yield. And one thing to remember when you're working with generator functions is that return stops a function, but the yield pauses execution, like it's frozen in time. So this is tricky when it comes to like questions that have like a line that may error after a yield function, after a yield statement within a generator function. So just be really careful when you're like looking at where the yield statements are and like what exactly is actually being evaluated. Calling a generator function automatically returns a generator object. The initial call to a generator function doesn't begin execution or step into the function at all. We need to call the next on the return generator object to begin stepping through. So that's another nuance to remember. Finally, yield from can be used with any iterable, and that'll yield the values of that iterable one at a time. So let's do what would Python do with generators. So given this code, let's think what each call to next would do. So does anyone want to like take a guess at what next gen object is going to do? What it'll yield? Yeah. Yep. And then if we call it again, what'll happen? Yeah. Yep. And then 2. And then eventually it'll just keep going until we hit the end of the for loop. At that point, where we hit the end of the function. And then if we call next again, we'll get a stop iteration error. So let's look at our first practice problem, yield Fibonacci. So in this one, we're basically implementing a generator version of fibs. It takes a one argument pure function f and yields all Fibonacci numbers x, for which f of x returns a true value. So the Fibonacci numbers begin with 0 and then 1. Each subsequent Fibonacci number is the sum of the previous two, and you should yield the Fibonacci numbers in order. So here are some doc tests, and then here's the skeleton. They're on different slides, so remember that we have the link to the presentation posted in the chat, and I think it's also on the ed. So if you need both slides, like definitely keep that presentation open. But I'll like switch between them occasionally. I'll keep it on the skeleton code for now. But yeah, any questions? Otherwise, I'll give you guys like maybe 5 minutes to work on this. Does anyone still want the slide? Should I switch it back to the instructions? Would that be helpful? Okay, like 1 more minute and then we'll go for this. Okay, hopefully we made some progress with that question. So now let's go over it. So one possible strategy that you can think about this is that we want to keep yielding Fibonacci numbers one after another, right? So maybe we can use the while loop to our advantage. So we can go through each iteration, and then that way we can yield every single number. So for each loop, we want to update n and m to the next Fibonacci pair, and then we're never actually ending the loop because there's no upper limit to the Fibonacci sequence. But we don't have to worry about infinite looping, since like this is a generator function, and then yield is going to pause the function before each call. So like we'll evaluate up to the yield, and then it's only until we get the next call again that we'll evaluate the function until we hit the next yield. So if we do while true, that's how we get the never breaking while loop. That's going to be something you probably want to keep in mind. We can use while true in order to create like infinite generator functions. And then for each iteration, we want to update n to be m while simultaneously changing m to the next number of the Fibonacci sequence. So this is an example of how we can use multi-assignment to reassign multiple variables in one line. In my opinion, this is probably the trickiest part of this question. It doesn't show up too much, but it's also something just good to know. Basically, we're like, if you look at the side, like why the code runs differently if we do n equals m and then m equals n plus m. In that case, we would need like a temporary variable to like store in between. Otherwise, we're going to lose one of the values. But if we do multi-assign, we can actually just change all the values all at once without needing that temporary variable. So multi-assign is pretty useful like that. But now we want to figure out what we want to yield and when we want to yield. So if we recall from the instructions, we only want to yield n if applying the input function f gives true. So then that way we're only going to yield the numbers in the Fibonacci that actually match the predicate, that actually match the function. So if we do, so that's why we fill in if f of n, that's shorthand for f of n equals true. In that case, then we'll yield n. We yield n and we're checking n because the Fibonacci sequence starts from 0. And if we do like f of m, we're never actually checking f of 0. And then we would end up skipping 0 even when it's a valid number. So that's why we have to be really careful about the variables we're using. But overall, that's the kind of the idea here. Hopefully that kind of makes sense. Any questions? Okay, let me check the chat if there's any questions. Okay, I'm not seeing any questions in the chat or in the Q&A. So we'll move on to the next problem. This one is a little trickier. All links. So implement a generator function all links, which takes nums, a list of equal length lists. All links should yield all linked lists S that can be constructed such that the first element of S is the first element of one of the lists in nums. The second element of S is the second element of one of the lists in nums, and so on. Lists can be yielded in any order. You can assume that nums is a non-empty list. So let's take a look. This is a question where taking a look at the doc tests can be really big help. So let's look at that. So for the second doc tests, all links 0, 2, 1, 3, there are 4 total linked lists we should yield. So the first list is link 0 and then link 2. That's generated from using the first element from the first list and then the second element from the first list. Link 0, link 3 is generated with the first element from the first list and the second element from the second list. Link 1, link 2, and link 1, link 3 get the first element from the second list and the second element from the first and second lists respectively. So you can kind of think as we're creating a bunch of combinations of linked lists, but there's a very particular way we're doing that. So I know this seems a little like confusing at first, but once we look at the skeleton code, that might help you figure out how to get started with this. So here's the skeleton code. Yeah, I'll give you guys like around like maybe 5 or so minutes to work on this. Since how are we doing on time? Okay, we're doing okay on time. Okay, maybe a little more than 5 minutes, but here's the skeleton code. And then here are the doc tests. I'll keep it on the skeleton code for like the first 2 minutes and then I'll go back to the doc tests. So yeah, if you have any questions, feel free to put it in the chat, put it in the Q&A, or if you're in person, just raise your hand. But yeah, so definitely do look at the doc tests and yeah. Okay, maybe like 2 more minutes and then we'll move on. Okay, so let's go over this problem. So a couple things that I would notice right off the bat, and hopefully that you did too, is that because we're looking for like different choices for selecting which items in which lists to yield, that's usually a pretty dead giveaway that we need to use recursion. Also because there doesn't really seem to be any way we can like generate all those lists just using this one function, like iteratively. Like yeah, like you should look at this and probably think we probably need to be using recursion. And then you can also kind of see that they already give you the base case through the if and else statement. The base case in this case is if length of nums 0 equals 0, then we need to do something, but we're not quite sure what we need to do. Because right now, like we know that there's never going to be an input that actually like matches that. So we can come back to this and see how we can use the base case later. So now our question is, how can we simplify nums in order to eventually reach the base case? Since what is nums again? Nums is a list of lists. Yeah, a list of equal length lists. So we want to simplify nums in order to reach that base case. So one idea we can go for is by reducing the lists in nums by recursively slicing off the first item. So in the first for loop, we can see that x of 0 is already selected in the list comprehension. So we can do something with first, while the rest should be the rest of nums. So we can take the slice of each x in nums by using slice notation. And then that way we just get a list of lists minus the first item from each of the list of lists. And then in the for loop, we're taking the first item from each of those list of lists and then doing something with that. So how can we find all the possible links from rest? Well, we can make a recursive call. At this point, we should be thinking about how we're putting everything back together, because we're basically building up these linked lists up until we get all the valid combinations that we want. So yeah, let's think about how we can use that recursive call now that we have like our list comprehension set up and also, yeah, our first and rest set up. So all links rests is going to return an iterator that yields each item one at a time. That we can then append each first, which is again element 0 of each list in nums, to each item, which is the link object yielded from all links of rest inside the double for loop. So I know that's kind of confusing. So like what's being yielded is basically we can assume that that's already like some sort of well-formed linked list that we're going to tack on like the first item to. And then that way we can just build up every combination of possible linked lists. So yeah, then we have 2 blanks left. So now we need to think, how can we make this work for when length of nums 0 equals 1, which is again the first doc test, and how can we append first to the beginning of a link object? So for the last line, we can yield link first comma item to create a new link node that contains first and connects the rest of the linked list. So that's how we're putting everything back together. And then we yield link.empty in the base case, because when length of nums of 0 is 1, then rests is just a list of empty lists, and that matches the base case. And that also kind of makes sense, right? If we look at like the else condition, and then we look at if we think about if we're yielding and we're yielding like all the way at the bottom, we want to start by building off of a link.empty and then repeatedly tacking on items onto that in order to like construct our linked list. So that's kind of why our base case makes sense intuitively. We want all links rest to just return link.empty, so we can yield link first comma link.empty for each first. So yeah. Any questions? Okay, it doesn't seem like there are any in the chat either. So let's move on to, I think this is our last question for iterators and generators. This is fall 2022, final question 7. I remember doing this last semester. But in Penny's game, 2 players each choose a different sequence of 3 coin flips, heads or tails. A coin is flipped repeatedly until one of those sequences occurs. The winner is the player whose sequence is flipped. Here's an example. Player 1 selects the sequence heads, 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 and player 2 selects the sequence tails, heads, heads. Then a coin is flipped repeatedly, yielding the following sequence of coin flips. And it's that string. And since tails, heads, heads was flipped first, which is also the last 3 flips, player 2 wins. So here's the question. We want to implement the generator function 3 flips. It takes an input A, which is it takes as input a potentially infinite iterator, which is called coin, and each element of which is either heads or tails, well, the H character or the T character, which denotes the coin flips of heads and tails respectively. It yields a sequence of triples of coin flip outcomes from coin. So here's our skeleton code. And like, again, like this, in this case, it would be really helpful to take a look at the doc tests. So we see that A is this iterator, it takes in this iterator that's HTT, HHT. And when we call next on A, we get coin flips 0, 1, and 2, which is HTT. And then when we call next again on this generator function, we get coin flips 1, 2, and 3. We can see we've like actually like dropped off one and then added one. And then it's yielded that sequence. So take a look at the doc tests. That's my big hint to you. And then think about how we can fill in the skeleton using this. And if you have any questions, again, feel free to raise your hand, put it in the chat. I'll give you guys maybe 4 or so minutes to do this. Okay, like 1 more minute. Okay. Hopefully we made some progress on that. Let's go over this problem. So if we look at the doc tests, like I think I kind of gave this away at first, but we want to yield 3 consecutive flips each time, and start is what we yield. So we want to assign that first 3 flips to start. And remember that coin is an iterator over the string. And every time we call next on the coin, we're going to get a character back. So if we call next on coin 3 times, then we can build a string that's of 3 characters of length. And then that's going to be the first 3 flips, the first 3 flip results of that coin, which is what we want. So we call next 3 times on coin, and then that creates like the initial starting string of like 3 results, which is what we get. So yeah, like coin flip 0, 1, 2, next on A, HTT, like all matches with the doc test, right? We always want to be looking back at the doc tests. And then again, like we kind of talked about this earlier, but because we know that the coin iterator, it could be infinite, right? So how can we create like an infinite generator function? Well, we can just put the yield statement inside a while true loop, because that loop is never going to end. So whether or not our generator is infinite or not depends on the input coin. If coin is infinite, the generator can also be infinite. We use while true here to support this case. And then if coin is not infinite, the generator would stop like the doc test as well, since when we call next on coin, a stop iteration exception would be raised. And then finally, if we look at the doc test again, we see that the generator yields flips 0, 1, 2, and then 1, 2, 3, and then 2, 3, 4. So in each case, we're removing the first flip, which is also the first character in the variable start. And then we keep the next 2. We keep the second and third flips, and then we tack on a new flip by calling next on coin. So we can do that by like taking a substring from start by doing 1 colon. That gets us the first character and everything onwards, and then we can add on next coin, which is going to be a character, and then that'll give us an updated sequence of like 3 flips, which is again what we want. So then every time we're calling next on A, we're going to be getting, we're dropping the first flip and we're adding a new flip to the end. But yeah, any questions? Okay, cool. That's it for iterators and generators, and next is object-oriented programming.
Hi, everyone. My name is Christina. I will be going over object-oriented programming. I just wanted to thank you guys for hanging in there. I know it's kind of late on a Sunday night, but we really appreciate you guys coming out here, and we know that this is going to help with your studying. So to start off with object-oriented programming, OOP is basically used to help organize our data and also combine the representation with their functions or behaviors. So one example of a class is a car class, and it's a template from which objects can be instantiated from. So in this case, we have 2 car instances or objects, my Lambo and my Toyota. So these are basically specific instances of a car class. So they're like actual physical cars, while a car class is just like a template of which you can build cars up. Down here, you can see that in order to create an instance, we use the car class with a capital C, and we use empty parentheses in order to call the init method. So next we have class variables and methods, which are shared among all objects of the same class. So for example, for a car class, we might have, for example, all cars have 4 wheels, while an instance variable is specific to a particular object. And if a class and an instance have the same attribute, then the instance will override the class attribute method. For example, below we have a class implementation of car in which the color of the car is blue. But then down here, if we create a car called Lambo and then we change the color to red, then we will have that the Lambo.color will be red. So in this case, the instance will override the class attribute color. But if we call car.color, we will still get blue. And if we were to create a new car afterwards, we would still get that the color of the new car would be blue, even though we changed the color of Lambo to be red. Here are some important OOP methods to remember. So these 3 methods are called implicitly, which means that we won't necessarily call them by like calling init or repr or stir, but when we're creating a car class, we will just be using the constructor implicitly. So init is the constructor that initializes a new instance of an object. Repr is the official string representation of object. So when we print out just an object, that's what we will be using is the repr method. And then stir or string is the human readable representation of object. So it's used for when we print an object. Do we have any questions so far? So next I'll talk a little bit about inheritance. So inheritance describes relationships that exist between classes and their subclasses, and this is often explained as a parent and child relationship. So subclasses or child classes inherit all the methods and attributes of a parent class and are also able to add their own. However, parent classes cannot access the attributes and methods of their children. Inheritance follows a is-a relationship. So for example, a Lamborghini class would inherit from a car class because a Lamborghini is a car. So in this case, Lamborghini is the child class and then car is the parent class. However, a car class would not inherit from a Lamborghini class because not all cars are Lamborghinis. You wouldn't say like a car is a Lamborghini. So for example, we have Toyotas, Ferraris, Mini Coopers are also cars, but they're not Lamborghinis. So it's always important to remember the relationship between classes, so then you can use that knowledge in order to look up certain methods or variables in the parent class. Here are some tips and tricks when dealing with inheritance problems. So first of all, you can either use super.method or class.method to access the parent class's method. But remember that when you're using super, you don't need to pass in self because using super basically initializes an instance, while using the class name itself, you would have to pass in the instance afterwards in the parentheses. Another tip to remember is that when you're checking for an attribute, you want to check the object instance itself to see if it has that attribute. And if not, you would check the class of that instance and then the parent of that class and keep going up the chain. And if you reach the parent class and there's no attribute, then you would get an attribute error. Any questions? Okay, finally, we have some more OOP tips and tricks. So when we're working with OOP, we always want to use dot notation to call methods. And the two ways we have for using dot notation for methods is class.method and then passing in the instance, or we can just call it directly from the instance using instance.method. So in the second case, you wouldn't need to pass in self because we're already referring to the instance in the beginning, but using the first method of using class.method, we would need to pass in self, which would be our instance that we're referring to. Next, we always want to read the doc test when starting OOP problems. They can be really helpful when telling you exactly the relationships between different classes, the outputs of methods, and specifically for stir and repr methods, they usually tell you like exactly how those are defined and what they want for both of those methods. Another tip is to draw out diagrams representing classes and their instances. I really like doing this, especially for instances, and it helps you remember like if an instance attribute has been overridden from a class, and also to keep track of like all the different instances you have of a certain class. When writing methods for classes, make sure that the first parameter you're passing in is self. Likewise, don't forget to use self dot when accessing attributes and methods. Any questions so far? We'll work on our practice problem now. So we're going to be looking at the summer 2022 midterm question 8. I actually did this midterm question last summer. So it says Tyler and Chris are representing their restaurant sales with different food classes that should be item classes. In order to track their sales, implement the boba class. Boba are items in the restaurant. When a new item is created, that item's name should be added to the class attribute dictionary, all items with a value of 1 in the class item. And if the name is already in the dictionary, you should increase the value by 1. And boba should have a list, all boba, that stores all the boba items that have been sold. And boba's topping attribute keeps track of what topping that drink had, if any. So I'll give you guys a couple minutes to work on this problem and then we'll regroup. Okay, for the sake of time, we'll start going over this. Don't worry if you didn't get to finish it. I know that wasn't a lot of time. So to start off, I think with this problem, it is really important to look at the problem statement because it tells you a lot about how to solve the problem. So first of all, when reading through the problem statement, it says boba are items in the restaurant, and that kind of gives you a hint as to inheritance, as in boba is an item in the restaurant. So we know that our class boba will inherit from the item class. Any questions? And next, we'll just go down blank by blank. So all boba, we can see is a variable inside our class, so it's a class attribute. And in our problem statement, we see that boba should have a list all boba that stores all the boba items that have been sold. So we can set all boba to be an empty list at first. And next, we're going to be looking inside our init method. And we know that since boba is a subclass of item, we can call the init method of our superclass in order to basically do this work for us without having to rewrite it in our boba class. So one way we could do that is writing super.init with name, cost, and stock, which is basically passing the same arguments as in the init method of the item class. And another way we could do this is item.init self name, cost, and stock. So this is, like we said before, using the item class name itself. And in this case, since we're using the name of the class instead of super, we do need to pass in self, which is basically our instance that we're constructing. Next, we're going to initialize a new topping instance variable, self.topping. And this is kind of showing how in a child class or a subclass, you can have like new instance attributes specific to that class. For example, not all items have toppings, but since boba usually does have toppings, you can have a self.topping instance attribute. And next, we're going to want to do boba.allappend, all boba.append self, and this is taking care of the line boba should have a list all boba that stores all the boba items that have been sold. So in this case, when we're creating a new boba item, we're going to want it to append it to our class attribute list all boba by doing boba.all boba.append self. And it's important to remember that when we're accessing all boba, we need to call boba in the beginning or self in order to access that class attribute. So we could do it either with the boba class or just self, because an instance will have access to that class attribute, but we need to remember to either use boba dot or self dot in front of all boba. Any questions so far? And next we'll be taking care of the all items dictionary. So in the problem statement, it says when a new item is created, that item's name should be added to the class attribute dictionary all items with a value of 1 in the class item. And if the name is already in the dictionary, the value should increase by 1. So now we can check if self.name is not in item.allItems, then we're going to want to create that key with self.name and set it equal to 1. And here we want to note that we have a lot of possible solutions. So instead of self.name, we could use name because name is an argument passed it. So we are able to access it just using name. But I think for like convention, and usually you want to use self.name whenever you're referring to an instance attribute. And instead of all items, we could also say boba.all items, self.all items, or super.all items. And this is because, again, boba is a subclass of items. So it's able to access that all items attribute by doing variable lookup in its parent class. And finally, if the name is already in all items, then we're just going to want to increase the value by 1. So we would do item.allItems self.name plus equals 1. And same thing here. We could also use boba.allItems or self.allItems or super.allItems. Do we have any questions on anything in this boba problem? Cool. The next question is about F strings, and I think I'll just walk through it because I know we haven't gotten a lot of like exposure to F strings in lecture and discussion. So in this problem, it says the dictionary entry class stores entries for an English dictionary using instance variables for the word and its definition. So we have youth, which is a dictionary entry with the word euphoric and the definition intensely happy, and then avid with the definition enthusiastic. And then we have a list containing youth and avid, and returning that list, we get dictionary entry euphoric, intensely happy, and dictionary entry avid, enthusiastic. And for the F string, today we are learning youth, we get today we are learning euphoric, colon, intensely happy. So in this case, it is important to read through the doc test and kind of be able to pick out whether we're referring to the repr method or the stir method. So whenever we're referring to it, just like printing, like just returning an object itself, for example, youth, then we would want to refer to the repr method. While in this case, whenever we're working with F strings or we're working with the print method, then we're going to be looking at the stir method of the object. So first off, we'll look at the repr method. So in this case, we'll be referring to the list containing youth and avid, which is just a list containing these two objects. So we'll be looking at how the object is represented as a string. And looking at this, we see that we want to get dictionary entry, parentheses, and then in quotation marks, euphoric, and then comma, in quotation marks, intensely happy, and then another comma. And that's kind of like how we want to represent our object. So in this case, since we want to use these like names euphoric and intensely happy, which are specific to a certain instance of a dictionary entry, we want to be using an F string so we can substitute those with the actual word and the definition for that instance. And just as a quick refresher, an F string basically allows us to substitute these variables like self.word and self.definition inside of a string. And it basically helps us like keep our code concise. But in this case, we see that instead of just doing self.word, we also want to add repr in front of self.word. And that's because we want to maintain these quotation marks inside our object representation. So since we want these quotation marks, we want to use repr in order to basically create a double set of quotation marks that will be maintained whenever we put this inside the F string. Any questions on that? I know F strings are like not covered a lot in class. Okay, and then next we have our stir method. And this one, we're going to be having our word first. And in this case, we don't have the quotation marks around it. So we can just do self.word inside curly brackets and then the colon, space. And since we want to have these double quotation marks, we can use the backslash in order to put these quotation marks in front and outside of the intensely happy. And since we wanted double quotes, we want to make sure that we use the backslash in order to escape the quotation marks and just have them print out as quotation marks. Well, in the repr case, since we wanted the single quotation marks, we could use repr self.definition. Any questions? Yeah.
What's the purpose of the slashes again around self-definition?
Yeah, so the backslashes are basically used to escape the quotation mark. So we don't treat them as a like quotation mark in order to end the F string, but instead we just treat them as like quotation marks within the F string.
Oh.
So it's like an escape character.
So it's kind of like a reverse of that. It's like rather adds the quotes around and
This one actually doesn't get rid of the quotes. It adds the quotes inside the F string, but it makes sure that we don't like escape the F string. So these quotes are still maintained within the F string.
Oh, okay.
So I recommend maybe putting down like an example or two on your cheat sheet of like how F strings work and also like translating that into like how just writing it out with strings would work and concatenating them. Any other questions? Next, we'll move on to linked lists.
Hi everyone, I'm Chloe. I'll be presenting on linked lists. So what are linked lists? Essentially, they are data structures that store sequences of values, similar to a lot of other data structures. But for linked lists specifically, they consist of links, which each store two attributes. Firstly, the value, we call that first, and a pointer to the head of the rest of the list, we call that rest. Rest can either point to another link or the class attribute link.empty. It shouldn't point to anything else, only one of those two options. And it must traverse through the list using the pointer stored in rest. So unlike arrays where you can index into a specific part of it that you want, with a linked list, say you want to access item 5, you need to go through 0, 1, 2, 3, 4 first. So here's the class definition. So you can see we have the constructor as usual. Rest equals link.empty is set as a default if you don't give it a rest when initializing the list part. So we assert rest as link.empty or is instance rest link. And you have self.first rest, self.first equals first, self.rest equals rest. Since linked lists are similar to Python lists, how can we make 1, 2, 3 except this time with the linked list? We'll see here. You have the head of the list, and you connect that to another link instance where the first value is 2. And that one with rest points to another link instance where first is equal to 3. And at the end, since we have no more values, rest points to link.empty, and that completes the linked list. And here we have our variable s pointing to the head of the linked list, and we can use that variable s to access the linked list and the rest of its components. So here are some examples of how you would access parts of the linked list, s.first, for example, and s.rest. So why do we have linked lists? Essentially, what can they do? So their most basic functions are to access the first or the value that the pointer link holds, and then access the rest of it from there on. So we iterate and traverse through the values of a linked list in sequential order. We can mutate the values as we go through it, we can copy it to another data structure, or we can search for a specific value. Again, links are just a value and another link. So when you do all the exam problems, which usually involve a lot of recursion, think about the base case with linked lists, which we'll do in another example. So say we have the linked list s equals link 5, 7, 9, 11. The index of 5 is 0, so it's like arrays. The index of 7 is 1, the index of 11 is 3. So in practice, we don't do this s.rest.first thing in general. Maybe for exam questions you might, but this is technically considered bad practice. So in the example, we're going to implement the function filter index, which takes a 1-argument pure function f and a link instance s. It then returns a link containing all elements of s that have an index I, for which function I returns a true value. So here are some doc tests. Say we have the linked list powers with the values 1, 2, 4, 8, 16, 32. So that's the powers of 2. When we apply filter index, we only want x smaller than 4, we get the first 4 values. And when we filter it by the index where all odd indices, essentially you get 2, 8, 32. We just go every other item in the list. So here's the skeleton code for the filter index function. As you can see, there's some pointers here when you're trying to work through the question. We can take about like 7 minutes for this, I think. So some things to consider would be, what does I represent? When we are given skeleton code, one of the best things to start with is, what do all these variables mean? And from there, how can I actually use them to solve the rest of the problem? So in this case, like how and when should we increment I once we know what I represents? What does our recursive call look like? What does it usually look like with a linked list? What do we do if the function is true? And what do we do if it's not? And why do we even need another function inside of the master function? I'll give you guys like maybe a minute to finish up. All right, so I think we'll start going through the question now. So we'll go through these things to consider. It'll help us problem solve as we go through. So firstly, does anyone want to say what I represents in the helper function? Okay. So in this question, we're trying to go through the indices of the linked list. And here I refers to the index that we're currently working on. And how and when should we increment I? We increment it within the recursive call to update the index. So unlike some functions in the skeleton code, there isn't a clear if-else suite where we put the recursive call. Instead, we put the recursive call into the variable filtered rest. Oftentimes, these variable names are informative for a reason. You can look at them to try and infer what should go into that variable. In this case, filtered rest refers to we're going to apply the helper function to the remainder of the linked list that we're not looking at right now. So filtered rest equals helper I plus 1 s dot rest. We increment it by 1 because the index increases by 1, and we're working with the rest of the linked list. So what do we do when fi is true, which means that the function that we're given is true for that particular index? We return link s dot first filtered rest because if the function is true, we want to keep that index, the value at that index, and we add it to the final linked list that we'll return. You can see here we use filtered rest as s.rest because that's what we want to return. So why do we need that helper function? Why can't we just use one master function? It's because we need to track one more variable for this question specifically. So we want to track the index, which filter index would not allow us to do. So you can see we return helper 0s because we start at index 0, and s is the linked list that we're given. Before I move on to the next question, are there any questions? Okay, great. Let's move on. Linked list example 2. So here we're going to implement the function combine2. It takes in a linked list of integers and a function fn which takes in 2 arguments. So we're going to return a new linked list where every 2 elements from linked is combined using that function. So here we have the list 1, 2, 3, and combine2 adds every pair of elements in the list. So as you can see, 1 plus 2 is 3, so that creates 3 and 3. Since we have an odd number of elements, 3 is just added on at the back. Link 2 equals 4, 1. When we combine it using multiply, we get 4, 6. So here's the skeleton code. Some more useful things to consider would be what is our base case in this scenario, or perhaps base cases. How many arguments does the function fn take in? What does our recursive call look like, and where is it in this function? What do we do if it's true, and what do we do if it's false? We don't have helper in this case, but yes. So take about 5 minutes to try this out. We'll take another minute and then we'll discuss. All right, let's go ahead and discuss the problem. There's not many lines to fill in here, so, all right. So first of all, how many base cases do we have with this problem? 2, right? Because we have 2 different situations where either we have an odd number of items in the linked list or we have an even number. And we need to check that we either 1, still have 2 elements left to work with, or 2, we only have 1 element left to work with in which we cannot use the function. So in this first case, if link is link.empty, meaning we have had an even number of items put into the function, we return link.empty as our usual base case. And for this one, link.rest is link.empty, return link.first, because we just add the remaining element at the end that doesn't go into any fn call. So these are 2 of the most common base cases when working with linked lists. Either we check that the list itself is empty or the rest of the list is empty. And here's our recursive call with combined. Similarly to the previous problem, we apply the function onto link.first and link.rest.first. So we're combining the first 2 elements that we have in the list. And then we return link combined to link.rest.rest because we're adding on the combined part. And then we're making a recursive call on the rest of the list starting from rest.rest because we've just processed the first 2 elements in the linked list. Does anyone have any questions? All right, we'll move on then. Oh, sure.
Actually, so what I did is I did combine it was essentially like the whole return expression, except instead of combine it in that whole expression, and then I did return combine. Is that also?
Yeah, that should also work, but try to stick to the skeleton for exam problems. So here they want you to separate. It's called combine because they want you to just apply the function to the first 2 and then make the recursive call in the return statement. But
it was intending to apply that.
Oh yeah. Okay. So now we'll move on to some past exam problems. First one, bedazzled. So we're going to implement the function make necklace, which creates a linked list where every value comes from a given list of beads, and the beads are repeated in order to make a necklace of a given length. For example, here, if we call it with the linked list above and a length of 3, it will create this linked list because it repeats once we get to the end of the linked list and starts the beads again. So here are some doc tests. Take about like 5 minutes for this question, and then we'll discuss. The tricky part with this question is thinking of, you can see we have very little spaces, but we need to move through the list and we need to restart from the beginning when we get to the end of the list. I think that's the hard part of this. So think about how you can use what you know about the list structure when making the recursive call in the last line. Take about another minute. No, okay. Let's look at the question. So there are really only 5 blanks for something that feels like there should be more blanks, but okay, our usual base case length equals 0, as you might expect. That's when we don't need to add any more beats. We just return link.empty so that we complete the linked list. So one thing to always remember is to ensure the linked list ends with link.empty. I think that's something that's overlooked pretty often. So here's the recursive case. We return link beats 0. So we take the front of beats. And here's the tricky part. Our recursive call involves taking all the elements except the first one from beats and then adding that first one to the back because we've just added that onto the necklace. So essentially we've taken the first beat, we've added it to the necklace, and now we're moving it to the back. So every time we take an element, we move it to the back and so on and so forth. So that uses slicing as was discussed earlier. And then we return length -1. That one's a bit more straightforward because we're reducing by 1. We've already added 1 beat. Is this clear with everyone? Okay. Recursive leap of faith. You're just going to assume the rest of the bracelet works out. That's another good thing to remember when doing linked list problems. Okay, and here's our last question for linked list comprehension. We're going to generate a list from another list, just like we use list comprehensions normally with arrays. So we call the expression a mapping expression and the if clause a filter clause in, oh, we're just ending, okay. Trees. Sorry, we're running out of time, guys.
Hi everyone, I'm Balaji. So yeah, we are running a little low on time. So I'm going to try to speed through this as fast as I can. It might be like 5 to 10 minutes over, but I will talk as fast as I can while being somewhat coherent. But yeah, trees. So, I mean, we've gone over trees a lot. The one thing that we see kind of later in the course, like recently, is that trees are actually data structures that store hierarchical data. So it's not just tree recursion, but you can take data and then put it into a tree in a certain pattern that sort of makes sense, and you can do operations on it based off of that. And so as we know, a tree has a root label, which is usually a number string, and then a sequence of branches. These branches in and of itself are also trees, which is why a lot of people like to say trees are a recursive data structure, because each branch is a tree in and of itself. And a tree with no branches is called a leaf, which actually leads me into the next slide, which is the tree class. So because of object-oriented programming, we can take our tree and put it into a class to make it a little bit easier to work with. Each tree is going to have a label, like I mentioned, and a list of branches. In order to check if a tree is a leaf, you're gonna, when it says return not self.branches, it's checking, hey, is self.branches empty? If it's empty, then by putting the not in front of it, you're actually returning true because there are no branches to the tree. The important thing for this sort of like class API is really not to memorize any of this, because it's given to you, and it's more so like, what is each thing doing? So when am I going to use is leaf? When am I going to use tree.label? That's really the more important thing. And so what I'll definitely say is, in order to really understand how to do any of these, it's just going to be a lot of practice. You can use the reference guide, but it's going to be a lot of practice. Highly recommend doing practice tests. So working with trees. So because each branch of a tree is also, a tree, you're going to have to do a good amount of recursion, almost always recursion. And so in order to think, when you think about a recursion problem, right, the base case usually is when you hit a leaf node, or you don't really need to operate on the tree any further. Usually, I mean, like if you've seen, it's usually like if tree is leaf, usually along those lines. There are problems that are a little bit different. The parentheses actually are really important here. So oftentimes you'll have an explicit base case where you'll say like if t is a leaf, but there are also times where you can actually not have an explicit base case and it's sort of implied within your code. Usually this comes up, and actually one of the problems it'll come up, but usually this comes up if a list of branches is empty, which I'll get into soon. And then if you don't hit your base case, right, if you're in the middle of your tree, or if you're at the root node or something, there's still parts of the tree that need to be operated on. And so you're going to have to call a recursive method on it, on each of the branches usually. So when you're working with trees, there's really two different ways to think about it. First things first is when you're creating a tree from another tree. The example they give here is actually really important. So create a new tree with all labels doubled. So if you are given a tree with a bunch of labels and nodes, and you have to create a new tree with each of the labels doubled, what you're really doing is you're operating on the original inputted tree. You're given a tree and you're doubling each of the nodes, but you're storing the result in a brand new tree. This is actually kind of what we learned initially before mutation came along, where you're creating a new tree and storing whatever you've operated from the original tree. The second thing is creating a tree from a tree recursive problem. So I like to think of this more so as usually the problem will give you like some sort of pattern, or they'll give you a tree and say, this is the pattern that the tree needs to follow. How can we do this? Write code so that this tree will be converted to follow a certain pattern. One of the problems later on actually does this, and so I'll mention that there. The example they give here is the Fibonacci tree, right? So this is the whole point of the Fibonacci tree, is that there's a pattern. Each of the nodes add up to the parent node, right? So 1 and 0 down here add up to 1, 1 and 1, 2, 2 and 1, 3. And so like this could be the example of the second one, where you're basically given a pattern and given a tree, and you have to basically fix quote unquote your tree to make sure that the pattern works. Some tips for tree problems. I mean, there's 4, but I will say like the 0th one is just like, no matter how much you like look at these tips, it's more so just practicing them and explaining it to yourself, because the way we explain it might make sense for certain people, but a lot of people just like to explain it to themselves in a different way. first things first is remember that you can now edit branches and labels directly. This is mutation. So rather than if your label of your tree is changing, you don't have to say new tree now. You can just say tree.labels equal to 5, 6, a string, anything like that. The second point is keep in mind that you can mutate the label of a tree before or after the recursive calls. So generally, when you think about, a recursive statement or a tree recursive statement, usually what might come to mind is, hey, I'm going to edit my, I'm going to change my root node, and then I'm going to apply recursive call to each of its branches. But you can also do like a bottom up approach where you're editing all of your branches first, and then only are you changing your root node. And to really understand that, like the Fibonacci tree is a great example of that, because in order to figure out what the root node is, you have to figure out what these two are. In order to figure out what these two are, you have to figure out what each of those branches are and what each of those branches are. So you're basically figuring out and operating on the branches before you even go up to the root node, which is what I like to call like bottom up. Third, if you want to edit the branches of a tree, think about the tools you have for manipulating lists. So at the end of the day, although we have OOP, trees in and of itself are lists, right? So you can still use list comprehensions for being T-dot branches, slicing, indexing, all of those list comprehension techniques. And this is the last point, is just to make sure, like, this is something that a lot of people get like points off, and it's just like a silly error, honestly. The problem will tell you, hey, am I going to mutate the tree that I'm given, or am I creating a new tree that stores whatever I've operated on the original tree? This, although the processes might be the same for both, there are certain nuances in terms of syntax that you're going to have to do in terms of if you're mutating the tree versus creating a new tree. Any questions on that before we get into problems? Okay, cool. So example 1, they give you a big definition, but I'll just explain it. So a level order traversal of a tree is what I like to consider like you're basically visiting each node from the top down and left to right. So what I mean by that is you first start at 1, and then in the second row, right, there's multiple, so you go left to right, 2, 3, 4. Then you go to the next row, 5, 6, 7, 8, 9. And so that's how you quote unquote like visit. In this problem or in the next problem, it's you're yielding, but so your level order traversal of a tree in this tree would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so our objective is to fill in level order, a generator function to yield the labels of a given tree in level order. The strategy is to use a helper function, which is one level, that yields nodes at one level, and then to call this function with increasing levels until level does not yield any labels. It says you may not need all the lines. You don't need one of the lines. One level, I would definitely recommend trying one level and figuring out what one level is, and then using that function in the bottom here. But let's give it about 5 minutes. Might have to cut you a little short, but oh yeah, and there's going to be a practice, like midterm practice question that I'm not going to cover just for the sake of time, but I definitely recommend looking at that after. But there's going to be one more small problem after this. Give it like 2 more minutes. Okay, for the sake of time, I'm just going to start now. This is a really hard question, and I definitely didn't give you enough time, but it is what it is. So first things first is I would definitely look at one level, which is going to yield all of the nodes at a certain level. And so I like to think about it in terms of a tree. So if I go back to this example, this is 5, 6, 7, 8, 9 is level 2, right? If we're at level 0, we immediately yield, what's there, right? Which is 1. If we're at level 2, what's really going to happen is we're going to have to first, basically check, hey, am I at level 0? 0 here. I'm not. Then I go down to here. Am I at the correct level here? No. And then do I go down to here? I'm at the correct level. So when we pass in if we pretend K is 2, right? Level 2, then I'm basically going to have to go down each level of the tree until I hit the correct level, which is why K double equals 0 is going to be our base case. And I'll explain that a little bit more once we get into the else statement. But essentially, once we get to the right level, we're going to be yielding that tree's label. Now, how does this make sense? It's really because if we're not at the right level, then you're going to basically iterate through each child in the levels branches. So for example, in this case, if we're at level 1, right, and we're not at the right level, then we're going to have to iterate through each of its level, each 2, 3, 4's children, and call one level on it. Why that makes sense is because we're actually decrementing K by 1. So each time we go down a level, because we're going down in terms of children, we're actually going down a level and we're decrementing K by 1 until K hits 0. So when K is 2 at the top, right? When K is 2 at the top here, nothing really happens and you call one level on each of these. Here, nothing really happens because K is still 1. And only here, when K is equal to 0, are you yielding your tree labels. And what so happens is you actually do yield it left to right just because of how this code works. Okay, so that's one level. That's how you can generate the labels of a tree at level K. But now how can you implement this in terms of the level order function? So first things first is to note the level is equal to 0 initially. So you're starting at the top and count is equal to true, meaning that while count loop is going to work. This line is left blank. This is the line I was talking about that you don't necessarily need. But then the important part is the for label. So for label in one level, tree level, what that really means is I'm going to iterate through each level's nodes. Initially, that level is 0, right? So I'm going to iterate through the top nodes, which is just 1. And each time I do this, I'm going to do something, I'm going to yield something, and then I'm going to go down to the next level and yield all of those. And this is how we basically do that. So I want to ignore count plus equals 1 just for a second and go down to yield label. So we're iterating through each of the nodes at a certain level, let's say 0 or 1, and we're yielding those labels. And so one level yields from left to right. And so when we yield these labels, we're also going, first like top row and then left to right of the second row, left to right of the third row, et cetera, et cetera. The reason we have count plus equals 1 is it's important to look at the actual visual representation. So each time there is, let's say, a node at a certain level, this is level 2, right? There's nodes at this certain level. So each time there's a node, you're going to increment count by 1. So 1, 2, 3, 4, 5. By the end of this for loop, count is equal to 5. And then what happens is the next time you're going to have for label in one level tree at level 3. The problem is, notice that there is nothing at level 3, right? Nothing exists in level 3, which actually turns out to be our base case. Because when you iterate through like one level tree at level 3 will return an empty list, meaning that for label in empty list will just return nothing and you won't yield any labels and it'll stop there. So that's what I was mentioning about the base case being implicit. Oftentimes what happens is once you get to a certain point in your tree, it'll become an empty list and you're iterating through an empty list, which will stop your code from recalling a recursive function altogether. Any questions? This is a confusing problem, but good. Okay. This is a much quicker problem. Just for the sake of time, I'll just finish with this. So prune tree, which destructively prunes a tree T so that the sum of each path from root to leaf is less than or equal to total. I think probably it's better to look at the visual. So notice how this tree turns into this tree because total in this case is 6, right? And let's take a look at like this branch right here. 1 plus 6 plus 2 is going to be equal to 9, which is greater than 6. So you prune it, aka completely get rid of it. 1 plus 2 plus 2 plus 1 is going to be equal to 6. So you can keep that. And so that's the whole point of the problem. You're taking, this is sort of like our second version of tree operations. You're taking a tree and basically pruning it, you're editing it to make sure that a certain pattern follows. So let's take, for the sake of time, let's take like 2 minutes and then I'll quickly go over this and then we can call it a day. Like 30 more seconds. Okay. So this, as you can see, it's deceptively in 3 lines. So there's going to be a lot of code in at least one of them. And that turns out to be the first line. B for B and T dot branches if T dot label plus B dot label is less than or equal to total. So we should probably break this down. So first things first is we see that we're iterating for B and T dot branches. So we're iterating through the branches of a tree. And then our list comprehension keeps it as just a branch if t.label plus b.label is less than or equal to total. What that means is, for each of these branches, if 1 plus 2 is less than or equal to 6, we keep the branch 2 and all of its subparts for now. Same thing with 3. 3 plus 1 is less than 4, less than or equal to 4, so we keep it. What we see here, though, is 6 plus 1, right, is not less than or equal to 6. 7 is not less than or equal to 6, so we don't keep it in our list comprehension. And essentially, we're setting t.branches equal to just these two branches here, which we see on the right? So it's, although you're not like deleting a list element, you're basically setting t.branches equal to a new list with the correct branches. And then what we have to do is, not only do we have to check these branches, we have to check each of these branches and each of these branches, right? We have to check all the nodes. And so we iterate for b and t.branches. So for each of these branches, we're going to call prune tree of b total minus t.label. So the prune tree of b should make a little, should bring up a little bit of memory in the sense that, we're iterating and calling a recursive function on each of the branches. But why are we doing total minus t.label? Well, think about it in this sense, right? Our sum is going to be from root to leaf, meaning that if you're in this branch right here, whatever sum this is, you're going to have to add that to 1 and then compare that to total, right? Meaning if total is 6 here, that means that whatever here is, that has to add up to at max 5 or below. And that's why we do total minus t.label. In this case, it would be 6 minus 1, so this would be 5. That's why if you notice here, or at least here, the 4 is gone. Why? Because 2 plus 1 plus 2 is equal to 5, you're set. 3 plus 2 is equal to 5, you're set. But 4 plus 2 is greater than or equal to 5, and you prune that out and you get rid of that. And so in that sense, you're basically at each level, you're decrementing the amount of total based off of which node you're coming from. Any questions on that? Okay, so this question, exam question 3 is on spring 2022. I would highly recommend taking this whole test. It's really, really helpful. And it tells you a lot, but yeah, thank you for coming. Thank you for staying a little bit extra. And yeah. Cool.
That's the one on the exam. Remember to keep trying to take a lot of practice exams. Take at least 1 per day out of leading up to the exam, and try to go into the exam with fresh mind. And on the day of the exam, try to not do any practice exam. Try to just go with a fresh mind, with a happy mind, and best of luck on the exam.
Thank you.